In the quiet reaches between galaxies, where light thins into a pale memory, a vast shape drifts through the dark. It moves without sound, without urgency, carrying the remnants of ancient stars that were already old when Earth was young. This is Andromeda, a cosmic giant approaching across the void, its slow advance unfolding over billions of years, so gradual that only the sensitive instruments of modern astronomy can trace its motion. For most of human history, it appeared as nothing more than a faint, blurred smudge hanging in the night sky. A fragile cloud that seemed too delicate, too small, to redefine the scale of the universe. Yet within that fragile cloud lay a truth waiting to be uncovered, one that would stretch the human imagination outward into an ocean of stars. A century ago, Edwin Hubble measured the flicker of distant Cepheid variables inside this pale smudge and realized that Andromeda did not belong to the Milky Way. It was not a nearby nebula, but an island universe unto itself, a sprawling galaxy millions of light-years beyond the boundary of everything once known. And with that discovery came a deeper question, one that lingered like a shadow behind every new observation. How large is this silent neighbor? How far does its influence extend into the dark? Now, for the first time, astronomers have traced the full outline of its hidden structure, charting not only the glittering disk of stars but the immense, invisible halo that surrounds it. And the answer is larger, stranger, and more consequential than anyone once imagined, large enough to reshape our understanding of galactic architecture, of dark matter, and of the quiet, inevitable collision that awaits the Milky Way. In the earliest centuries of recorded skywatching, long before astronomy became a science of instruments and equations, the night was a vast canvas painted by myth. Stars were interpreted as omens, stories, ancestors, or gods. And in this tapestry of points and patterns, there existed a single delicate blur, a faint mist that seemed out of place among the sharp, glittering constellations. Ancient Persian astronomers noted it without explanation. Medieval observers, using nothing more than the naked eye, listed it among the curiosities of the sky. Greek star catalogues referred to it as the little cloud, an object without structure or meaning. To those early observers, Andromeda was neither threatening nor profound. It was simply dim, delicate, and easily ignored. Yet that small smear of light would become one of the most important clues in humanity's quest to understand the size of the universe. The journey from cloud to cosmos would take centuries, guided by visionaries who slowly peeled away the layers of the unknown. As telescopes entered the world in the 17th century, the faint blur solidified into a soft glowing oval. Astronomers such as Simon Marius and later Charles Messier described Andromeda as a nebulous object, a cloudy patch without the crisp features of stars. Some speculated that these nebulas were regions where stars were forming. Others believed they were swirls of gas within the Milky Way. The idea that this faint object could lie outside our galaxy was too bold, too vast, to be seriously considered in an age when the universe was still imagined as relatively small. In the 19th century, as telescope lenses grew larger and mirrors more precise, Andromeda began to reveal hints of structure. The English astronomer William Parsons, the third Earl of Rosse, armed with the Leviathan of Parsonstown, then the world's largest telescope, sketched the first recognizable spiral form within the nebula. Its sweeping arc suggested that it was not merely a cloud but an organized system. Still, most astronomers believed it belonged inside the Milky Way, perhaps as a whirlpool of stars forming in the galactic outskirts. The scale of the universe was assumed to be limited. The Milky Way was thought to contain everything. But some voices questioned this assumption. In 1755, Immanuel Kant proposed that the faint nebulas might be island universes, systems of stars far beyond the Milky Way. It was a brilliant intuition, centuries ahead of observational proof. Yet without precise measurements of distance, the idea remained philosophical speculation, drifting at the edge of scientific imagination. The breakthrough would come not from speculation but from light itself, from the rhythmic brightening and dimming of a rare type of star known as a Cepheid variable. Cepheids serve as cosmic beacons. Their pulsations reveal their intrinsic brightness, and by comparing that brightness to how faint they appear, astronomers can determine their distance. They were the key to unlocking the size of the universe. In the early 20th century, Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory, focused this powerful instrument on Andromeda. The images he captured contained unexpected anomalies, tiny points of light that flickered with periodic precision, Cepheid variables. Their patterns were unmistakable, and when Hubble calculated their distance, the results were staggering. These stars lay far beyond the Milky Way, far beyond everything humans had ever imagined. Andromeda was not a cloud, not a gas whirlpool, not a region of star birth within our galaxy. It was a separate galaxy, a vast, rotating island of stars millions of light-years away. The universe, suddenly, was hundreds of times larger than anyone had dared to believe. In 1923, Hubble announced his findings, and the paradigm of astronomy shifted overnight. The cosmos was no longer limited to the Milky Way. It was a landscape of countless galaxies scattered across an immense expanse. And among them, Andromeda stood as one of the nearest giants. The revelation ignited a new era of exploration. If Andromeda was a galaxy, then its shape, size, and structure mattered. Astronomers began charting its spiral arms, searching for clusters, supernova remnants, and cold dust lanes. Photography became a vital tool. Long exposures captured features invisible to the naked eye. As the decades passed, radio telescopes added new layers of understanding, tracing the rotation of hydrogen gas within the galaxy's disk. From these observations emerged a deeper and more unsettling question, a suspicion that the visible portion of Andromeda, the glowing spiral captured in early photographs, might not be the galaxy's full extent. Something unseen seemed to tug on the stars. Their rapid rotation, especially at the edges of the disk, suggested more mass than the luminous material could account for. This discrepancy hinted at an invisible structure surrounding the galaxy, something vast and mysterious. The groundwork for this suspicion was laid in the 1930s by Fritz Zwicky, who proposed that galaxy clusters contained unseen mass. Later, in the 1970s, astronomer Vera Rubin found that stars in spiral galaxies, including the Milky Way, rotated too quickly to be held together by visible matter alone. The same physics applied to Andromeda. The galaxy's stars moved through space as though swimming in a massive, hidden halo, a sphere of unknown material extending far beyond the visible spiral. The search for this invisible structure became a defining pursuit of late 20th century astronomy. Instruments like the Hubble Space Telescope, launched in 1990, began capturing unprecedented details of Andromeda's stellar streams, long, ghost-like trails of stars ripped from smaller galaxies. These streams hinted at the gravitational shape of the unseen halo enveloping Andromeda. Observations of its satellite galaxies, its globular clusters, and its diffuse gas clouds provided further clues. Each piece suggested that Andromeda extended much farther than the eye could see. Meanwhile, ground-based surveys such as the Sloan Digital Sky Survey deepened the mystery. They uncovered thousands of stars far outside Andromeda's visible disk, many of them belonging to tidal streams or ancient collisions. These faint tracers acted as breadcrumbs marking the edge of the galaxy's gravitational influence. With each new discovery, the suspected size of Andromeda grew larger. By the early 21st century, astronomers realized that the faint spiral visible in telescopes was merely the luminous heart of a far greater organism. Andromeda's true structure, shaped by dark matter, cosmic evolution, and billions of years of galactic mergers, sprawled across an immense region of intergalactic space. The question that had once seemed simple, how big is Andromeda, became one of the great astronomical puzzles. It was a question that could not be answered through light alone. It required understanding the invisible, the gravitational, the theoretical. It required examining the motions of stars at the edge of detectability, the distribution of dwarf galaxies in orbit around Andromeda, the faint arcs of debris from past collisions. It required looking not only at what was present but at what was missing, the hidden mass that bound the galaxy together. From ancient star catalogs to modern cosmology, Andromeda's evolution in human understanding reflects the evolution of astronomy itself. What began as a faint smudge became a spiral, then a galaxy, then a gravitational titan with a footprint far beyond anything early observers could have imagined. And with each revelation, the suspicion grew stronger. The visible disk might be only the beginning. The mystery of Andromeda's true size was now open, waiting for deeper exploration, waiting for the tools, the theories, and the discoveries that would eventually reveal how vast this approaching giant truly is. In the decades following Edwin Hubble's revelation, astronomers believed they finally understood what Andromeda was. A neighboring spiral galaxy, larger than the Milky Way and shaped by the same cosmic processes that governed all galaxies. Its glowing arms, dust lanes, star clusters, and bright central bulge appeared to offer a complete portrait of its structure. Yet just beneath this sense of clarity, a new and unsettling realization was forming, one that would upend the quiet confidence of early galactic science. As telescopes improved and radio astronomy rose to prominence, astronomers began to measure the motions of stars and gas within Andromeda's disk. These observations revealed something unexpected. The stars at the edge of the spiral arms were moving far too quickly. According to Newton's laws and Einstein's refinement of gravity, material at the outskirts of a galaxy should orbit more slowly than material near the center. Gravity, weakening with distance, should allow distant stars to drift in wide, leisurely arcs. But this was not what Andromeda revealed. The galaxy's rotation curve, a plot of orbital speed versus distance, refused to decline. Instead, it flattened, even rose slightly, as though invisible hands were holding the outer stars in their tight, rapid motion. If the galaxy contained only the mass represented by its stars, gas, and dust, these outer regions should have flown apart long ago. Andromeda appeared to be rotating in violation of classical expectations, as though the universe itself were rewriting the rules of gravity. This contradiction triggered the first scientific shock. Either the galaxy was embedded within a vast, hidden reservoir of mass, or the fundamental understanding of gravity was incomplete. It was a tension that echoed across the scientific world, forcing astronomers to choose between rewriting physical law or accepting the presence of something immense and unseen. These were tidal streams, remnants of dwarf galaxies that had ventured too close to Andromeda's gravitational well and had been torn apart over billions of years. Their stars, once bound together, had been scattered into long, curving filaments that traced the invisible contours of the halo. Each stream acted like a celestial antenna, detecting the shape of the dark matter around it. Next came data from the Hubble Space Telescope, whose deep-field instruments pushed the search even farther into the cosmic dimness. Hubble's sharp vision could isolate individual red giant stars nearly 1 million light-years from Andromeda's center. These stars were faint and sparse, drifting in remote corners of the halo where the night was nearly empty. Yet their presence carried immense significance. They served as markers, traces of ancient collisions, echoes of galaxies that had passed too close and left fragments behind. With each new stellar detection, the halo's boundaries grew outward. What had once been imagined as a modest sphere surrounding the visible galaxy now appeared almost planetary in scale, enveloping vast regions of intergalactic space. Andromeda's gravitational influence was far-reaching, ancient, and intricate. Further evidence arrived from globular clusters, spherical swarms of tens of thousands of old stars, tightly bound and resilient. Many clusters orbit close to the galactic center, but some wander through the outer halo like lanterns drifting through a dark ocean. By measuring the velocities of these distant clusters, astronomers could infer how much unseen mass was holding them in orbit. Some clusters were found on elongated, looping paths reaching almost 300,000 light-years from the core. Their motion suggested a halo far heavier and larger than early models predicted. Still, the most dramatic discoveries came from tidal shells, ghostly arcs of stars arranged in sweeping, concentric layers. These shells formed when small galaxies collided with Andromeda long ago, their stars thrown into looping trajectories that caused them to pile up at certain distances, forming rippling patterns of light. Each shell was a fossil of past interaction, a record of cosmic cannibalism preserved in starlight. These features revealed not just the size of the halo, but its history, a long sequence of mergers and encounters that had shaped Andromeda's evolution. The halo was not smooth or uniform. It was scarred, layered, and dynamic, carrying the remnants of galaxies that no longer existed except as faint trails woven through the dark. The most significant advancements came when astronomers began to combine all these observations, stellar velocities, tidal streams, globular clusters, and shells, into cohesive 3D maps. Using sophisticated models, they reconstructed the motions of tens of thousands of stars, tracing their orbits backward in time to reveal the invisible gravitational field guiding them. The emerging picture was extraordinary. The halo was not a simple sphere, but a massive, extended structure reaching more than 1,000,000 light-years in diameter. It blended near its edges into the domain of the Milky Way's own dark matter halo, creating a vast, overlapping region where the influence of both galaxies intertwined. This realization carried profound implications. It suggested that Andromeda and the Milky Way were not isolated giants drifting toward an inevitable future collision. They were already part of a shared ecosystem, two galaxies embedded in a continuous field of dark matter that shaped the local group as a single, interconnected entity. But the investigation did not end there. The arrival of new survey missions, including Pan-STARRS and the Hyper-SuprimeCam project in Hawaii, enabled astronomers to observe the faintest edges of the halo with greater clarity. These instruments detected star streams so dim that they were nearly invisible against the background sky, revealing filaments stretching hundreds of thousands of light-years across. Some streams were nearly straight, others sharply curved, each one shaped by Andromeda's gravitational field in complex and beautiful ways. One of the most striking discoveries was a sprawling structure known as the Giant Stellar Stream, a massive ribbon of stars extending more than 300,000 light-years. Its size alone hinted at a powerful gravitational environment, one capable of capturing and reshaping entire dwarf galaxies. Models suggested the stream was the shredded remains of a galaxy that had passed close to Andromeda long ago, its orbit guiding it through the dark matter halo like a thread pulled through an unseen loom. The stream became a cornerstone of halo studies. By calculating its orbital path, astronomers could estimate the mass distribution of the dark matter surrounding Andromeda. The results consistently pointed toward a structure far larger than its visible disk, heavy enough to bind dozens of satellite galaxies in long, graceful orbits. These satellites, including Andromeda 1, 2, 3, and many others, provided additional clues. Their motions revealed they were not simply wandering companions, but objects moving through the halo's deep gravitational valley. Some traveled in coherent planes, suggesting ancient alignments or shared origins. Others appeared to be in the process of being absorbed, slowly disintegrating as Andromeda's unseen mass pulled them apart. Each discovery expanded the boundary outward. Each new piece of evidence reshaped the estimate of Andromeda's true size. What began as a luminous disk of a few 100,000 light-years had become a sprawling, dark matter-dominated sphere nearly 10 times larger. Yet the halo's final edge remained difficult to define. Dark matter did not stop abruptly. It faded gradually, blending into the ambient density of the local group. The boundary, therefore, was not a line, but a gradient, a slow merging of gravitational influence. Scientists sought to identify a virial radius, a distance where the halo could be considered bound and stable. Estimates placed it between 800,000 and 1.3 million light-years, a staggering dimension that made Andromeda one of the largest objects in the cosmic neighborhood. As the investigation deepened, a pattern emerged. The more astronomers measured, the larger Andromeda seemed to become. Every new technique pushed the edge farther outward. Every deeper observation revealed structures more distant and more fragile than expected. And beneath it all lay a simple, humbling truth. The majority of Andromeda's mass lay beyond the reach of human eyes, shaping a gravitational cathedral that only the most sensitive instruments could perceive. The luminous galaxy was a brilliant but incomplete portrait, a central flame surrounded by a vast and silent domain of dark matter. By mapping the unseen halo, astronomers were not merely tracing the boundaries of a galaxy. They were uncovering the architecture of the universe itself, a universe where light is only the surface, and where the true shape of cosmic structure lies hidden in the dark. And still, The investigation pressed onward, for the greatest revelation was yet to come, a measurement of Andromeda's full size, one that would redefine its place in the local group and reshape humanity's understanding of the vast cosmic space between galaxies. These were tidal streams, remnants of dwarf galaxies that had ventured too close to Andromeda's gravitational well and had been torn apart over billions of years. Their stars, once bound together, had been scattered into long, curving filaments that traced the invisible contours of the halo. Each stream acted like a celestial antenna, detecting the shape of the dark matter around it. Next came data from the Hubble Space Telescope, whose deep-field instruments pushed the search even farther into the cosmic dimness. Hubble's sharp vision could isolate individual red giant stars nearly 1 million light-years from Andromeda's center. These stars were faint and sparse, drifting in remote corners of the halo where the night was nearly empty. Yet their presence carried immense significance. They served as markers, traces of ancient collisions, echoes of galaxies that had passed too close and left fragments behind. With each new stellar detection, the halo's boundaries grew outward. What had once been imagined as a modest sphere surrounding the visible galaxy now appeared almost planetary in scale, enveloping vast regions of intergalactic space. Andromeda's gravitational influence was far-reaching, ancient, and intricate. Further evidence arrived from globular clusters, spherical swarms of tens of thousands of old stars, tightly bound and resilient. Many clusters orbit close to the galactic center, but some wander through the outer halo like lanterns drifting through a dark ocean. By measuring the velocities of these distant clusters, astronomers could infer how much unseen mass was holding them in orbit. Some clusters were found on elongated, looping paths reaching almost 300,000 light-years from the core. Their motion suggested a halo far heavier and larger than early models predicted. Still, the most dramatic discoveries came from tidal shells, ghostly arcs of stars arranged in sweeping, concentric layers. These shells formed when small galaxies collided with Andromeda long ago, their stars thrown into looping trajectories that caused them to pile up at certain distances, forming rippling patterns of light. Each shell was a fossil of past interaction, a record of cosmic cannibalism preserved in starlight. These features revealed not just the size of the halo, but its history, a long sequence of mergers and encounters that had shaped Andromeda's evolution. The halo was not smooth or uniform. It was scarred, layered, and dynamic, carrying the remnants of galaxies that no longer existed except as faint trails woven through the dark. The most significant advancements came when astronomers began to combine all these observations, stellar velocities, tidal streams, globular clusters, and shells, into cohesive 3D maps. Using sophisticated models, they reconstructed the motions of tens of thousands of stars, tracing their orbits backward in time to reveal the invisible gravitational field guiding them. The emerging picture was extraordinary. The halo was not a simple sphere, but a massive, extended structure reaching more than 1 million light-years in diameter. It blended near its edges into the domain of the Milky Way's own dark matter halo, creating a vast, overlapping region where the influence of both galaxies intertwined. This realization carried profound implications. It suggested that Andromeda and the Milky Way were not isolated giants drifting toward an inevitable future collision. They were already part of a shared ecosystem, two galaxies embedded in a continuous field of dark matter that shaped the local group as a single, interconnected entity. But the investigation did not end there. The arrival of new survey missions, including Pan-STARRS and the Hyper-SuprimeCam project in Hawaii, enabled astronomers to observe the faintest edges of the halo with greater clarity. These instruments detected star streams so dim that they were nearly invisible against the background sky, revealing filaments stretching hundreds of thousands of light-years across. Some streams were nearly straight, others sharply curved, each one shaped by Andromeda's gravitational field in complex and beautiful ways. One of the most striking discoveries was a sprawling structure known as the Giant Stellar Stream, a massive ribbon of stars extending more than 300,000 light-years. Its size alone hinted at a powerful gravitational environment, one capable of capturing and reshaping entire dwarf galaxies. Models suggested the stream was the shredded remains of a galaxy that had passed close to Andromeda long ago, its orbit guiding it through the dark matter halo like a thread pulled through an unseen loom. The stream became a cornerstone of halo studies. By calculating its orbital path, astronomers could estimate the mass distribution of the dark matter surrounding Andromeda. The results consistently pointed toward a structure far larger than its visible disk, heavy enough to bind dozens of satellite galaxies in long, graceful orbits. These satellites, including Andromeda 1, 2, 3, and many others, provided additional clues. Their motions revealed they were not simply wandering companions, but objects moving through the halo's deep gravitational valley. Some traveled in coherent planes, suggesting ancient alignments or shared origins. Others appeared to be in the process of being absorbed, slowly disintegrating as Andromeda's unseen mass pulled them apart. Each discovery expanded the boundary outward. Each new piece of evidence reshaped the estimate of Andromeda's true size. What began as a luminous disk of a few 100,000 light-years had become a sprawling, dark matter-dominated sphere nearly 10 times larger. Yet the halo's final edge remained difficult to define. Dark matter did not stop abruptly. It faded gradually, blending into the ambient density of the local group. The boundary, therefore, was not a line, but a gradient, a slow merging of gravitational influence. Scientists sought to identify a virial radius, a distance where the halo could be considered bound and stable. Estimates placed it between 800,000 and 1.3 million light-years, a staggering dimension that made Andromeda one of the largest objects in the cosmic neighborhood. As the investigation deepened, a pattern emerged. The more astronomers measured, the larger Andromeda seemed to become. Every new technique pushed the edge farther outward. Every deeper observation revealed structures more distant and more fragile than expected. And beneath it all lay a simple, humbling truth. The majority of Andromeda's mass lay beyond the reach of human eyes, shaping a gravitational cathedral that only the most sensitive instruments could perceive. The luminous galaxy was a brilliant but incomplete portrait, a central flame surrounded by a vast and silent domain of dark matter. By mapping the unseen halo, astronomers were not merely tracing the boundaries of a galaxy. They were uncovering the architecture of the universe itself, a universe where light is only the surface, and where the true shape of cosmic structure lies hidden in the dark. And still, the investigation pressed onward, for the greatest revelation was yet to come, a measurement of Andromeda's full size, one that would redefine its place in the local group and reshape humanity's understanding of the vast cosmic space between galaxies. In the widening silence between the Milky Way and Andromeda, astronomers once imagined a vast emptiness, a tranquil gulf where galaxies drifted in isolation and light from one system faded long before touching the next. But as the 20th century drew to a close and new generations of survey telescopes swept across the sky, that imagined emptiness began to crumble. A different picture emerged, one in which the darkness was not a void at all, but a shared gravitational landscape shaped by two immense cosmic structures expanding far beyond their visible starlight. Andromeda had already revealed hints of hidden mass in its rapid rotation, but those early clues proved modest compared to what was coming. As astronomers pushed deeper into the outskirts of the galaxy, studying faint motions of distant halo stars and the subtle paths of satellite galaxies, a staggering realization formed. The unseen halo of Andromeda did not simply envelop the galaxy. It stretched outward in a vast, diffuse sphere that reached across intergalactic space. Research from surveys such as PANDAS, the Pan-Andromeda Archaeological Survey, provided the clearest view. Its deep imaging traced feeble arcs of stars looping across the sky, the remnants of ancient collisions with long-consumed galaxies. Many of these streams lay not tens of thousands of light-years from the disk, but hundreds of thousands, drawing an outline far larger than ever expected. Simulations backed the observations. To create such extended structures, Andromeda's dark matter halo had to be immense, perhaps spanning more than 1 million light-years from end to end. That scale changed everything. If the estimates were correct, the halo reached almost halfway to the Milky Way. And because the Milky Way possessed its own halo of comparable size, The two giants were not merely drifting toward each other, they were already touching, their invisible envelopes blending in the dark like two tides meeting far from shore. The local group, once thought to be a loose collection of galaxies, now appeared as a web of overlapping gravitational domains where the boundaries between one system and another became increasingly difficult to define. The implications of this discovery deepened the mystery. A halo so large meant that Andromeda's reach extended into regions long assumed to belong to no particular galaxy. Dwarf galaxies floating between the two spirals found themselves inside a complex gravitational terrain, tugged subtly by forces from both sides. Some, such as M32 and NGC 205, orbited Andromeda closely. Others traced wide, slow paths that seemed influenced not just by Andromeda's mass but by the combined pull of the local group's entire dark matter structure. New simulations showed how this overlapping halo environment might shape the fate of smaller galaxies caught between the giants. Their motions were no longer governed by simple orbits around a single parent. Instead, they moved through a gravitational landscape sculpted by billions of solar masses of unseen matter, a landscape that shifted slowly as Andromeda and the Milky Way drifted closer. Some dwarfs were predicted to fall inward, spiraling gradually toward Andromeda. Others would be drawn toward the Milky Way, depending on subtle differences in momentum and position across millions of years. The size of Andromeda's halo also held consequences for the material through which light travels. Intergalactic gas, once thought sparse and inert, interacted with the enormous gravitational envelope, heating as it fell inward and cooling as it drifted outward. Observations by the Hubble Space Telescope's cosmic origins spectrograph revealed hot, diffuse gas surrounding Andromeda, stretching out hundreds of thousands of light-years. Its structure hinted at turbulent flows shaped by ancient supernovae, magnetic fields, and the slow infall of matter over cosmic time. This gas played a quiet but critical role in galactic evolution. It served as a reservoir for future star formation, as well as a record of past interactions. Chemical fingerprints within the halo suggested that Andromeda had absorbed many smaller galaxies, spreading their enriched material across immense distances. The halo's structure, therefore, became a living archive, a fossil record not written in rock but etched across intergalactic space. Yet the most profound consequence of Andromeda's expanded size lay in what it implied about the future. The approach of Andromeda and the Milky Way had long been known, their converging paths measured by subtle Doppler shifts and precise motions of stars. But if their halos were already interacting, then their encounter had, in a sense, begun. Not through the dramatic collision of stars and gas that would one day reshape both galaxies, but through the quiet blending of two invisible spheres. Like the first touch of distant waves before a storm, the meeting of their halos hinted at the deeper transformations still to come. Astrophysicists studied simulations of the long-term future, exploring how overlapping halos might influence the timing and nature of the eventual merger. Dark matter, the dominant mass in both systems, acted as the unseen architect of this interaction. Its gravity guided the approach, slowed the motions of passing dwarfs, and subtly altered the angular momentum of the galaxies themselves. In some simulations, the overlapping halos created drag-like forces that hastened the eventual collision by tens or even hundreds of millions of years. In others, the interaction changed the orientation of the galaxy's spins, affecting how the final merger would unfold. Magnetic fields, too, played a role. Though faint and difficult to measure, observations suggested that both Andromeda and the Milky Way possessed large-scale magnetic structures extending far beyond their visible disks. As their halos overlapped, these fields likely interacted, creating vast regions of tangled magnetism that influenced the movement of charged particles and the behavior of intergalactic gas. Such interactions, while subtle compared to the overwhelming pull of gravity, added yet another layer of complexity to the growing picture of Andromeda's true scale. The deeper astronomers looked, the more the mystery expanded. Andromeda was no longer simply a spiral galaxy drifting toward the Milky Way. It was a cosmic leviathan, its influence stretching across distances once considered unimaginable. The halo, once a theoretical construct, became a tangible structure shaping the motion of galaxies, the temperature of gas, the flow of stars, and the future of the local group itself. And with each new discovery, one question grew sharper. If the halo reached so far, then where did Andromeda truly end? The classical definition of a galaxy, a system of stars, gas, and dark matter bound together by gravity, seemed insufficient. Boundaries, once drawn with confidence around the bright disk and bulging core, dissolved into gradients and transitions that extended into the darkness. The galaxy became a cloud of influence, fading slowly into intergalactic space rather than ending abruptly at any clear border. In this expanding picture, Andromeda transformed from a familiar neighbor into something far more enigmatic. Its true size was no longer measured in the radius of its visible disk or the extent of its spiral arms, but in the unlit depth of its halo, a structure that defied intuition, challenged assumptions, and reshaped the map of the cosmos in which the Milky Way resides. Andromeda's halo did not simply grow in their measurements, it expanded in their minds as well, forcing a re-evaluation of what a galaxy truly is and how deeply two such giants can influence the space between them. The mystery now stretched farther than the eye could see, a silent boundary growing outward into the dark, waiting for the next generation of telescopes to trace its edge, or to discover that the edge might not exist at all. In the vast architecture of the universe, even the simplest questions grow complex when examined closely. Among the most elusive is a question that appears deceptively ordinary. Where does a galaxy end? For centuries, the answer seemed obvious. A galaxy was the glowing disk or cloud of stars visible through early telescopes, a bright island isolated against the dark sea of space. But as instruments sharpened and new wavelengths of light revealed structures previously unseen, the old boundaries dissolved. A galaxy no longer resembled a sharp-edged island. Instead, it became a sprawling system whose true size stretched far beyond the reach of ordinary starlight. Andromeda sits at the center of this scientific shift. Its visible disk spans nearly 220,000 light-years, already twice the size of the Milky Way's observable structure. But modern observations show that this bright disk is only the innermost layer of something much larger, an intricate web of stars, gas, and dark matter that fades gradually into the surrounding void. The deeper astronomers look, the less certain they become about where Andromeda truly ends. To understand its boundary, scientists turn to several theories, each attempting to define a galaxy not by what it emits, but by how gravity shapes its surroundings. The first is the virial radius, a concept rooted in classical dynamics. It marks the region around a galaxy where gravity holds matter in a rough equilibrium, binding stars, gas, and dark matter together despite the universe's expansion. For a galaxy as massive as Andromeda, models from lambda-CDIM cosmology estimate this radius at roughly 300,000 light-years, large enough to contain dozens of dwarf satellites, tidal streams, and relics of ancient collisions. Within this boundary, the motions of stars obey the gravitational pull of the galaxy as a whole. Beyond it, matter begins to drift more freely, influenced as much by the gravitational field of the local group as by Andromeda itself. Yet even the virial radius fails to capture the full picture. Dark matter, which constitutes the majority of Andromeda's mass, does not end abruptly at any clean border. Instead, it forms a diffuse halo extending outward in a gradient, fading but never quite disappearing. According to cosmological simulations, the outer regions of this halo may reach nearly 1 million light-years, a span so broad that it blends with the halo of the Milky Way. This dark matter halo model suggests that the two great galaxies are not isolated systems, but overlapping structures already intertwined long before their luminous parts collide. Such an interpretation reframes the notion of size. In this view, Andromeda's true boundary is not a rigid shell but a gradual transition, defined by how the density of dark matter falls off with distance. There is no line to be crossed, only a slow diminishment of influence stretching into intergalactic space. However, the halo model is not the only way to define a galaxy's edge. A newer idea, known as the splashback radius, seeks a boundary not by brightness or mass density, but by motion. In galaxy clusters, astronomers have identified a sharp drop in the density of matter at the point where infalling material reaches the apogee of its first orbit before falling back inward, the splashback moment. Though originally developed for massive clusters, some researchers argue that a similar principle might apply to individual galaxies. If so, Andromeda's splashback radius could define the outermost limits of material still engaged in a coherent orbit around its center. Preliminary models suggest that this radius may lie even farther out than the virial boundary, encompassing streams of dark matter and gas whose motions are still shaped by the galaxy's gravity. If confirmed, the splashback radius would place Andromeda's edge at distances surpassing 1,000,000 light-years, pushing the galaxy into a realm where the definitions blur and the local group becomes a continuous gravitational landscape. Another approach focuses on the stellar halo, the population of extremely faint, ancient stars scattered across the outer regions of a galaxy. These stars serve as luminous tracers of past mergers, their orbits stretching across vast distances. As surveys like PANDAS map their distribution, astronomers find shells, streams, and clumps extending outward nearly as far as the virial radius, and in some cases beyond. The density of these stars decreases gradually, offering no definitive boundary. Instead, the stellar halo becomes a diffuse veil, hinting that the galaxy's true structure may fade into the dark over hundreds of thousands of light-years. Each of these methods paints a different picture of Andromeda's size. According to the virial radius, the galaxy may span roughly 600,000 light-years across. The dark matter halo model doubles that figure. The splashback radius stretches it farther still, while the stellar halo offers no clear limit at all. In effect, Andromeda becomes not one entity but several, each defined by a different aspect of its gravitational story. This diversity in definitions has profound consequences for cosmology. It challenges the notion that galaxies are discrete objects with fixed edges. Instead, they resemble dynamic systems whose influence varies with distance and whose boundaries depend on the forces, matter, or motions being considered. The universe, viewed through this lens, becomes a continuum, a place where structures grade into one another, and where the distinction between one galaxy and the next is more philosophical than geometric. For Andromeda, this understanding reveals why estimates of its size vary so widely. The visible disk is only the bright core of a much larger organism. Around it lies a halo of stars shaped by its past, a halo of dark matter shaped by the universe's infancy, and a region of complex gravitational motion shaped by the slow dance between Andromeda and the Milky Way. No single definition can capture all of these layers. Each reveals only one facet of a larger truth. The ambiguity in Andromeda's boundary also reframes humanity's place within the local group. If the galaxy's halo extends nearly halfway to the Milky Way, then the two systems share a region of influence long before their eventual merger. A star drifting through this intergalactic corridor moves not through empty space but through overlapping gravitational domains. Gas clouds in this region respond to both galaxies at once. The faintest relics of ancient collisions drift across boundaries that do not truly exist. In the coming years, new telescopes will refine these measurements. The Vera Rubin Observatory will trace faint stellar streams with unprecedented detail. The James Webb Space Telescope will probe the oldest stars in the halo. Future gravitational lensing studies may map the dark matter distribution directly. Each advance will bring Andromeda's edge into sharper focus, or perhaps reveal that the edge is not a line at all, but a concept shaped by the questions astronomers choose to ask. And so the mystery persists. The size of Andromeda is not a single number. It is a spectrum of possibilities extending outward into the dark, each grounded in physics yet none definitive. The galaxy becomes a lesson in cosmic humility, that even familiar neighbors can stretch beyond human intuition, and that the universe thrives not on simple boundaries but on gradients, transitions, and unseen layers woven into the fabric of space. In this vast perspective, Andromeda does not end where its starlight fades. It ends where gravity relinquishes its hold, a boundary that shifts depending on how deeply one looks and how far one measures. And as astronomers explore these shifting definitions, they uncover not only the true scale of a galaxy, but the complexity of a universe where nothing stands alone and everything blends into the next. In the search for Andromeda's true size, nature offered no simple clues. The galaxy remained wrapped in darkness, its visible stars tracing only a thin lattice of brilliance across a far larger unseen realm. To measure a structure built mostly from matter that emits no light, astronomers needed instruments capable of reading subtler signs: the drifting paths of ancient stars, the chemical memories locked in their atmospheres, the slow gravitational tides that pull satellites into orbit, and the delicate curvature of space itself recorded across entire swaths of sky. Over the past 3 decades, a constellation of scientific tools emerged to confront this challenge. Each instrument contributed a different thread of information, and only by weaving all of them together could researchers begin to outline the true extent of the invisible halo surrounding Andromeda. The Hubble Space Telescope became the first pillar of this effort. Launched in 1990, Hubble could stare into the faint outskirts of the galaxy with unparalleled precision. Its long-term observations allowed astronomers to track the barely perceptible motions of individual stars and clusters drifting through Andromeda's halo. Over years, then decades, Hubble detected tiny shifts in their positions, changes so slight they amounted to the width of a coin seen from thousands of kilometers away. These shifts revealed the gravitational field sculpting their motions, offering a direct measurement of the mass pulling on them from deep within the galaxy. Each data point added subtle detail to a larger picture. Stars moving faster than expected hinted at hidden mass. Streams with unusual curvature traced ancient collisions, mapping the shape of the halo through their disruption. The farthest globular clusters, faint and worn by time, provided natural test particles orbiting the dark core of the galaxy. Through Hubble, the outskirts of Andromeda began to take shape not as emptiness, but as a dynamic region governed by a vast gravitational architecture. But Hubble alone could not measure the structure in its entirety. To understand how far Andromeda's influence extended, astronomers needed to study the galaxy's smaller companions, the dozens of dwarf galaxies trailing around it, each one orbiting under its gravitational pull. These satellites serve as markers around the periphery of the halo, their motions carrying the imprint of the unseen mass that binds them. The Gaia mission, launched by the European Space Agency in 2013, became the second pillar. Gaia's purpose was simple in concept but staggering in scale: to map the positions, distances, and motions of over 1 billion stars in the Milky Way and beyond. Over time, Gaia turned its attention to the local group, capturing the trajectories of Andromeda's satellite galaxies with a precision never before achieved. For the first time, astronomers could model the 3-dimensional movements of these dwarfs as they dipped and arced through the galaxy's gravitational field. Their speeds, directions, and accelerations revealed the mass distribution of the halo enveloping Andromeda. Some dwarfs moved in elongated orbits, stretching far into intergalactic space before curving back inward. Others drifted on paths distorted by interactions with the Milky Way. Together, their motions indicated a gravitational reach far greater than the visible disk suggested, a reach extending well over 1 million light-years. As Gaia refined the geometry of these orbits, 2 ground-based observatories added yet another layer of insight. The Keck Observatory in Hawaii and the Subaru telescope on Mauna Kea targeted individual stars scattered across Andromeda's halo. These stars, often relics of ancient mergers, contain chemical fingerprints in their atmospheres. The ratios of heavy elements within them reveal the histories of their parent galaxies, the collisions, star formation bursts, and tidal disruptions that created the halo's intricate structure. By measuring these chemical signatures, astronomers could distinguish stars formed within Andromeda from those captured during past mergers. The spatial distributions of these populations exposed the halo's true breadth. Wide streams of iron-poor stars traced the paths of long-dissolved dwarf galaxies. Shell-like structures encircling the disk hinted at past collisions that stirred the halo outward. These maps showed that the galaxy's influence extended far beyond even the most optimistic early estimates. With each new dataset, the halo grew larger, its outer edges pushing closer to the Milky Way. Yet even these measurements were not enough. Dark matter cannot be seen directly, and its distribution required models sophisticated enough to simulate the formation of galaxies from the earliest epochs of the universe. Cosmological simulations such as Illustris NG, and the Fire project became the final pillar of measurement. These simulations follow the evolution of dark matter and baryonic matter across billions of years, predicting how halos form, merge, and expand. They reveal that galaxies like Andromeda should possess halos with characteristic sizes tied to their mass and merger history. By comparing simulation predictions with observational data, star velocities measured by Hubble, satellite motions captured by Gaia, and chemical maps from Keck and Subaru, astronomers could infer the full extent of Andromeda's dark matter envelope. The models suggested that the halo must stretch between 1.3 and 1.5 million light-years in diameter, enveloping not only its satellite galaxies but a substantial fraction of the space between Andromeda and the Milky Way. In this convergence of data and theory, a coherent picture emerged. Andromeda, once a faint smudge glimpsed by early astronomers, evolved into a leviathan whose true size rivals or surpasses the Milky Way. Its dark matter halo, vast, diffuse, and gravitationally dominant, forms one half of a pair of overlapping spheres that define the local group. The space between the two galaxies, once assumed to be empty, became a shared gravitational frontier shaped by both systems. The most striking revelation was not simply the size of the halo, but the way these different methods converged on the same result. Hubble's star tracers, Gaia's satellite orbits, Keck and Subaru's chemical fingerprints, and the predictions from cosmological simulations all pointed to the same conclusion. The boundary of Andromeda lies far beyond its shimmering disk, reaching deep into the darkness where the Milky Way's own halo begins. This measurement carries profound implications. It suggests that the two galaxies are already interacting, not through their stars or gas, but through the silent pull of dark matter. Their halos may have touched long ago, beginning a gravitational interplay that will eventually lead to a full merger billions of years in the future. The local group becomes not a collection of isolated galaxies, but an interconnected structure bound by overlapping halos and shared dynamics. Ongoing studies continue to refine these measurements. Future datasets from Gaia will extend the tracking of satellite galaxies, revealing subtler motions shaped by Andromeda's deep gravitational field. Observations from the Vera Rubin Observatory will map faint structures across the sky, uncovering even more star streams reaching into intergalactic space. Gravitational lensing techniques will probe the outer halo directly, using distant galaxies as background lights warped by the mass of Andromeda. Each method will sharpen the estimate, but the broad conclusion has already taken firm shape. The galaxy, long thought to be modest in scale, has expanded into one of the largest structures visible from Earth. Its true size lies not in its glittering core, but in the shadowy halo surrounding it, a sphere of dark matter stretching more than 1 million light-years across. Through decades of observation, analysis, and simulation, humanity has finally measured this hidden structure. And in doing so, astronomers have revealed a cosmic truth. In the architecture of galaxies, the greatest forces work in silence, shaping boundaries that light alone cannot trace. In the quiet stretch of intergalactic space, where darkness outweighs starlight by 1,000 to 1, two ancient structures drift toward each other with the patience of stone. The Milky Way and Andromeda, each a spiral labyrinth of stars billions of years in the making, have begun a slow and silent convergence. Not through the blaze of collisions or the crack of cosmic upheaval, but through a whisper, the merging of their halos, the outermost realms of invisible matter that precede the galaxies themselves. To astronomers, this revelation reframes everything. The collision between both systems is not a distant drama waiting to unfold across 4 billion years. It has already begun. It is unfolding now, not in the bright visible disks of stars, but in the unseen framework that surrounds them. For more than a decade, models and measurements have shown that Andromeda's halo stretches outward for more than 1 million light-years. The Milky Way's halo, though less precisely mapped, reaches comparable scales. And somewhere in the quiet dark between the two spirals, these halos touch. To imagine this overlapping region is to picture a frontier without boundaries, an expanse where neither galaxy firmly rules, and yet both exert their pull. Here, stray gas clouds drift in the tug of competing gravitational tides. Rogue stars, long ago cast out by ancient mergers, orbit in paths gradually reshaped by forces that cross intergalactic lines. Even dwarf galaxies that once belonged unambiguously to one parent system may now feel a subtle, competing pull from the other. This is the first layer of the reflection. Humanity lives inside a cosmic relationship already underway. Earth, the Sun, the planets, all of them reside within the outer envelope of the Milky Way's halo, a region shaped by dark matter, long-range gravitational currents, and the faint detritus of ancient collisions. And now, that same region lies in the outskirts of Andromeda's expanding influence as well. The space humans inhabit is not isolated. It is not even the empty gulf once imagined between galaxies. It is part of a shared domain, a slowly tightening gravitational embrace between titanic structures rushing toward eventual union. From a scientific perspective, this deepens the understanding of what it means for galaxies to collide. The violent imagery that comes to mind, stars smashing, spirals unraveling, is not what awaits. When galaxies approach, the first contact occurs not between stars, but between halos. Invisible matter interacts gravitationally across distances too vast for light to map easily. Over billions of years, this gravitational bridge draws the galaxies closer and closer until their visible components finally meet. By the time the bright disks interpenetrate, the true collision will have been underway for eons. In the present day, this halo overlap subtly influences the motions of satellite galaxies on both sides. Tiny companions such as M32 and NGC 205 near Andromeda, or the Sagittarius Dwarf and the Magellanic Clouds near the Milky Way, follow orbits that respond not only to their immediate host galaxy but also to the gravitational landscape shaped by the other. Cosmic simulations show that such interactions can shift trajectories on the scale of billions of years, altering which satellites survive the future merger, which are torn apart, and which are absorbed into the growing streams of stars that will eventually lace the merged galaxies. These ideas reshape not just astronomy but human perspective. To understand the universe at this scale is to confront the fragility of familiar definitions. Words such as here, home, near, and far lose clarity when space itself becomes a gradient rather than a map of discrete objects. The boundary of the Milky Way is not a line but a transition, a thinning where its influence wanes and the influence of another grows. Andromeda is not a separate island. It is part of a shared ecosystem, a cosmic estuary where two immense gravitational rivers begin to mingle. This is where the reflection turns inward. Humanity measures galaxies in light years, velocities, mass estimates, and dark matter distributions. But the meaning of these measurements reaches far beyond numbers. They reveal that human existence unfolds in a place that is not static, not isolated, and not immune to the slow tides that shape the cosmos. Every planet, every star, every life form exists within a universe defined by motion. Motion so vast and gradual that it can be invisible to the senses, yet inexorable on cosmic scales. The overlapping halos of the Milky Way and Andromeda offer a reminder of this continuity. The night sky seems still, but the entire galaxy is moving toward its nearest giant neighbor, toward merger, toward transformation. The Sun traces a wide orbit around the galactic center, even as the galaxy itself drifts toward Andromeda at about 110 kilometers per second. This inward migration is not a threat but a natural evolution, one that countless galaxies undergo throughout the universe. For every spiral that has retained its shape, there are many more that have merged, intertwined, and reformed into something new. When astronomers say the collision will happen in 4 billion years, they speak of the moment when the bright stellar disks will begin to collide. But the merging of halos means that, in a quieter sense, the collision has already begun. Humanity lives inside a vast transitional zone, a precursor to a cosmic union that will one day reshape the stars themselves. Yet this knowledge does not bring fear. It brings perspective. The cosmic timescale on which these changes occur dwarfs the span of human civilization. Entire species may rise and fall before the first visible distortions appear in the night sky. Whatever humanity becomes or ceases to be, the merger between the Milky Way and Andromeda will continue its slow procession through time, untouched by the fate of any single planet. The universe is indifferent to urgency. It unfolds with monumental patience. And still, understanding this slow dance has profound meaning. It reveals that humanity is not merely observing the cosmos but participating in it, embedded within its ongoing evolution. Every star that will one day be part of the merged galaxy, sometimes called Milkomeda in scientific literature, is already drifting along a trajectory that shapes the future. The Earth is part of that trajectory. Knowledge of this connection offers a kind of belonging, a reminder that the human story is woven into the grand fabric of cosmic change. There is another layer of reflection as well, the importance of measurement itself. The size of Andromeda did not change when astronomers discovered its true extent. The galaxy did not grow. Humanity's understanding grew. What was once believed to be a neatly bounded island of stars is now known to be a structure so vast that its outer reaches blend with those of another galaxy entirely. This expansion of insight mirrors a larger trend in astronomy. Again and again, the universe reveals itself to be larger, more complex, and more interconnected than expected. When Hubble discovered the expansion of the universe, the cosmic horizon grew. When dark matter and dark energy were inferred, the cosmos became stranger and more profound. And now, as the concept of a galaxy's edge dissolves into a gradient of gravitational influence, the map of reality becomes even more intricate. Each new measurement adds detail to the picture, carving away assumptions and replacing them with structure and depth. And yet, beyond all the scientific implications, the overlapping halos of the Milky Way and Andromeda offer a poetic insight. Boundaries in the universe are rarely absolute. They are thresholds, transitions, zones where one identity fades into another. Galaxies merge. Stars exchange mass. Gas clouds drift between systems. Even in the vast emptiness of intergalactic space, the universe resists simple borders. The chapter closes on this idea. Not that the universe grows when galaxies expand or collide, but that the universe grows when understanding deepens. When humanity reaches farther into the dark and returns with new knowledge. When instruments refine the faintest signals and reveal connections that were always there, waiting to be seen. In the end, the true size of Andromeda is more than an astronomical fact. It is a reminder that the cosmos continues to unfold before human eyes, not through sudden revelations, but through steady accumulation of insight. It shows that the universe is not static, not silent, and not finished. It is a place where even the great spirals drifting through space are part of a larger story, one that stretches far beyond the lifespan of stars. And humanity, for a brief moment in cosmic time, has the privilege of watching that story unfold.